Hold out your hand. Look at it for a moment. Not quickly, slowly. The way you would look at something you had never seen before and were trying to understand. 5 fingers. Skin stretched over bone. Veins running beneath the surface carrying blood that is warm right now, in this moment, because a series of chemical reactions inside you are converting food into heat and motion and thought. It is ordinary. You have seen your hand 10,000 times. You have never once looked at it and thought, "This is one of the most extraordinary objects in the known universe." But it is. Not because of what it can do, though what it can do is remarkable. Not because of its complexity, though its complexity is staggering. But because of what it is made of. Because of where the material inside it has been. Because of the journey those atoms took before they arrived in your hand. In this moment, in this life. That journey is what we are going to follow today. It begins not on Earth, not in the ocean, where life first stirred, not even in the solar system. It begins in the first seconds of the universe. In a moment so far back in time that the numbers required to describe it have no meaning in ordinary experience. In a place that was not yet a place, in a time that was not yet time, in a heat so absolute that the word heat does not reach it. It begins at the beginning, and it ends with you. 13.8 billion years ago, the universe began. We will not spend time on what came before, because the honest answer is that we do not know. The physics we have breaks down at the boundary of the Big Bang. The question of what preceded it, or whether the word preceded even applies, is one that current science cannot answer. Or energy, barely distinguishable from the radiation that filled it. And then it began to cool. As the universe expanded, the temperature dropped. And as the temperature dropped, the particles slowed enough to begin combining. In the first microseconds, quarks bound together into protons and neutrons. The building blocks of atomic nuclei assembled themselves from the raw material of the early universe, held together by the strong nuclear force. By the time 3 minutes had passed since the Big Bang, just 3 minutes, the universe had cooled enough for protons and neutrons to fuse into the first atomic nuclei. Hydrogen, helium, traces of lithium. That was it. That was the entire elemental inventory of the early universe. 3 elements, in a ratio of roughly 3/4 hydrogen to 1/4 helium, with a whisper of lithium. Everything else, every element heavier than lithium, every atom of carbon, oxygen, iron, gold, calcium, phosphorus, did not yet exist anywhere in the universe. The atoms that would one day make up your body had not been created yet. They would have to wait. After those first 3 minutes of nucleosynthesis, the universe entered a period that cosmologists call, with appropriate poetry, the Dark Age. The atomic nuclei existed, but the universe was still too hot for electrons to bind to them and form complete atoms. The plasma of charged particles was opaque. Light could not travel freely through it. The universe was a fog, bright but unseeable from the inside, a glow without transparency. This lasted for approximately 380,000 years. 380,000 years of a universe filled with light that could not travel anywhere. A cosmos that was luminous but blind. And then, as the temperature dropped below a critical threshold, something happened that physicists call recombination, though it was not a recombination in the literal sense, since electrons and nuclei had never been combined before. The electrons slowed enough to be captured by the nuclei. Hydrogen atoms formed. helium atoms formed, and the universe became transparent. For the first time, in 380,000 years, light could travel freely. The fog lifted. The photons that had been trapped in the plasma streamed outward in all directions, and they are still traveling today, cooled by 13.8 billion years of cosmic expansion into the faint microwave glow we call the cosmic microwave background radiation, the oldest light in the universe. A photograph of the cosmos at 380,000 years old, still arriving at our instruments, still telling us what the universe looked like at the moment it first became clear. But the universe that became transparent was not the universe we know. It was still composed only of hydrogen and helium. It was smooth, almost featureless, with only the faintest variations in density from one region to another. And it was dark. The stars had not yet been born. In the darkness after recombination, gravity went to work. The slight variations in density that existed in the early universe, regions where the gas was fractionally denser than average, began to attract more gas. Slowly, over millions of years, clouds of hydrogen and helium accumulated, grew denser, contracted under their own weight. At the centers of these contracting clouds, the pressure and temperature rose, and rose, and rose, until somewhere between 100 million and 200 million years after the Big Bang, the temperature at the center of a contracting cloud reached the threshold, approximately 10 million degrees, at which hydrogen nuclei could overcome their electromagnetic repulsion and fuse together. The first star ignited. We have never seen these first stars directly. They existed too long ago, and the universe was not yet transparent in the same way it is now. But we can infer their properties from the physics, and what the physics tells us is that they were extraordinary. Because the gas from which they formed contained no heavy elements, no carbon, no oxygen, no anything that could absorb radiation and cool the collapsing cloud, these first stars could not fragment into the relatively small objects that stars typically form today. They grew enormous, masses hundreds of times that of our Sun, temperatures and luminosities that dwarfed anything in the modern universe. They were the largest stars that have ever existed, and they burned fast. A star like our Sun will live for approximately 10 billion years. These first stars, burning through their hydrogen fuel at an extraordinary rate, lived for perhaps 1 million years. A few million at most. In cosmic terms, they were born and died almost simultaneously. But what happened when they died is the reason you exist. Inside every star, a furnace operates. The furnace is nuclear fusion, the same process that generated the energy in the early universe, but now sustained in a stable environment by the pressure of the star's own gravity. In the core of a star, hydrogen nuclei fuse into helium, releasing energy that pushes outward against the inward pull of gravity. This balance, between the outward pressure of fusion energy and the inward pull of gravity, is what defines a star. It is what makes a star, rather than simply a very large cloud of gas. But fusion does not stop at helium. As a massive star ages, it exhausts the hydrogen in its core. The core contracts under gravity, the temperature rises further, and helium begins to fuse into carbon. When the helium is exhausted, carbon fuses into neon and magnesium, neon into oxygen, oxygen into silicon, silicon into iron. Each stage of this process requires a higher temperature and produces less energy per reaction. The star is working, harder and harder for diminishing returns, building heavier and heavier elements in its core in an increasingly desperate attempt to maintain the pressure that holds it up against gravity. This is where the atoms in your body come from. The carbon in every cell of your body was forged in the helium-burning shell of a dying star. The oxygen in every breath you take was made in the carbon-burning stage of stellar evolution. The calcium in your bones, the phosphorus in your DNA, the iron in your blood. All of it was manufactured in the nuclear furnace of a star that lived and died before the sun existed. You are not made of star stuff in the loose, poetic sense that phrase is sometimes used. You are made of star stuff in the precise, literal, chemically specific sense. The exact atoms in your body were inside a star. They were created by nuclear reactions that occurred at temperatures of hundreds of millions of degrees, in the cores of objects so massive they would swallow our entire solar system. And then something happened to release them. When a massive star, one with more than roughly 8 times the mass of our Sun, reaches the end of its fusion sequence, the end comes quickly and with extraordinary violence. The core has been building toward iron for millions of years. Iron is the end of the road for stellar fusion. Unlike lighter elements, iron does not release energy when it fuses. It absorbs energy. A star that begins fusing iron in its core is not generating energy, it is consuming it. The outward pressure drops. Gravity, which has been balanced by fusion pressure for the entire life of the star, suddenly wins. The core collapses. In less than a second, in approximately a quarter of a second, the core of a star that may have been as large as the orbit of Jupiter collapses to a sphere roughly 20 kilometers across. The density reaches the point where atomic nuclei are crushed together. Electrons are forced into protons, creating neutrons. A neutron star is born. And then the collapse bounces. The infalling outer layers of the star, still hundreds of thousands of kilometers of gas and plasma, slam into the newly formed neutron star and rebound outward in a shock wave of almost incomprehensible energy. A supernova. For a brief period, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. The energy released in a supernova in the first 10 seconds is greater than the total energy our Sun will emit over its entire 10 billion-year lifetime. And in the shockwave of that explosion, something else happens. The extreme temperatures and pressures of the supernova explosion drive additional nuclear reactions, reactions that create elements heavier than iron. Gold, silver, uranium, platinum. Elements that could not be made in any stellar furnace because their creation requires more energy than fusion releases. They are made in the moment of death, in the blast, in the brief instant when the energy budget of an exploding star is unconstrained by the need for sustainability. All the gold that has ever been worn as jewelry, all the uranium that has ever powered a reactor, all the silver in every photograph ever developed. It was all made in the deaths of massive stars, in supernova explosions scattered into space by the force of those deaths. And then the explosion fades, the light dims, the shockwave expands, the material, all those heavy elements, all that carbon and oxygen and iron and gold is thrown outward into the surrounding space at thousands of kilometers per second. A cloud of enriched gas, slowly expanding, slowly cooling, slowly mixing with the hydrogen and helium of the interstellar medium. Waiting, The atoms that would eventually become you spent a very long time in space, not doing nothing. Space is not nothing, even when it appears empty. Those atoms were part of vast clouds of interstellar gas, slowly drifting, slowly mixing, occasionally compressed by the shock waves of other supernovae, occasionally heated by the radiation of nearby stars. They cycled through generations of stars. A cloud of gas collapses into a star. The star burns for millions or billions of years, processing some of the gas into heavier elements. The star dies either gently for smaller stars which shed their outer layers as a planetary nebula, or violently in a supernova. The enriched material is returned to the interstellar medium. The universe is a recycling system of extraordinary patience and scale. Each generation of stars enriches the interstellar medium slightly more. The first stars left a universe with only hydrogen, helium, and traces of lithium. The second generation added carbon and oxygen and other light elements. Subsequent generations added more and more heavy elements, gradually building up the elemental richness that makes chemistry and life possible. By the time the solar system formed, approximately 4.6 billion years ago, the cloud of gas and dust from which it would form had been enriched by several generations of stellar evolution. It contained hydrogen and helium from the Big Bang, carbon and oxygen from the deaths of earlier stars, iron and heavier elements from supernova explosions, a full periodic table of elements, mixed together in a slowly rotating cloud, waiting for the right perturbation to trigger collapse. The perturbation came. Perhaps a nearby supernova sent a shock wave through the cloud. Perhaps a passing object disturbed it gravitationally. The exact trigger is not known. What we know is that the cloud began to collapse. 4.6 billion years ago, a cloud of gas and dust began to collapse under its own gravity. As it collapsed, it did what all collapsing clouds do. It began to rotate faster, the way a spinning skater pulls in their arms and accelerates. The cloud flattened into a disk. At the center of the disk, material accumulated and compressed until the temperature reached the fusion threshold. Our sun ignited. Around it, the remaining material in the disk began to clump. Dust grains stuck together. Clumps became pebbles. Pebbles became boulders. Boulders became planetesimals, the early building blocks of planets. Planetesimals collided and merged, building larger and larger objects, until the inner solar system was dominated by a small number of rocky bodies. One of them was the proto-Earth. The early Earth was nothing like the planet we know. It was a ball of molten rock, constantly bombarded by the remaining debris of the solar system's formation. The surface was a global ocean of magma. There was no atmosphere in any breathable sense. There was no ocean. There was no land. And then, approximately 4.5 billion years ago, a body roughly the size of Mars collided with the proto-Earth in an impact so violent that it melted both objects and threw an enormous quantity of material into orbit. That material coalesced into the Moon. The Earth, reformed from the debris of this collision, began to cool. The magma ocean solidified into the first crust. Gases escaping from the interior formed the first atmosphere, mostly carbon dioxide, nitrogen, water vapor. Comets and asteroids, still raining down from the outer solar system, delivered additional water and organic molecules. The atoms that would become you were here, in this world, from the beginning, not yet organized into anything living. not yet even organized into the molecules that life would eventually use. Just atoms scattered through the crust and the ocean and the atmosphere of a young, violent, inhospitable planet, waiting still for one more transformation. Approximately 3.8 billion years ago, perhaps earlier, the evidence is uncertain, something happened in the oceans of the early Earth that changed everything. Chemistry became biology. Molecules began to self-replicate. Collections of atoms arranged themselves into structures that could copy themselves, that could capture energy from their environment and use it to maintain and reproduce their own organization. The boundary between chemistry and life is not sharp. There is no single moment, no clear line. But somewhere in the warm, mineral-rich waters of the early ocean, in conditions we do not fully understand and cannot fully recreate, the first living things emerged. They were not complex. Single cells without even a nucleus. Organisms so simple that the word organism feels generous. But they were alive, in the sense that matters. They consumed energy, they reproduced, they passed information to their descendants. And they changed the planet. For the first 2 billion years of life on Earth, the dominant organisms were these simple, single-celled creatures. They evolved slowly, diversifying into thousands of forms, colonizing every available environment. And approximately 2.4 billion years ago, one lineage of them evolved a new capability, photosynthesis using water as an electron donor, a process that released oxygen as a byproduct. The Great Oxygenation Event. Oxygen, previously almost absent from Earth's atmosphere, began to accumulate. For the existing life forms, which had evolved in an oxygen-free world, this was catastrophic. Oxygen is chemically reactive and toxic to organisms not adapted to it. Most of the existing life died, but from the survivors, new forms evolved. Forms that could not only tolerate oxygen but use it to burn food more efficiently, to generate more energy, to power more complex biological processes. The atoms in your body passed through all of this. Through the first single cells, through the Great Oxygenation Event, through every evolutionary transition that followed. The first eukaryotic cells, the first multicellular organisms, the first animals, the first vertebrates, the first creatures to breathe air, the first to walk on land. Every form of life that has ever existed on this planet has been a temporary organization of atoms that were here long before life began and will be here long after life ends. You are one such organization, the latest in a line that stretches back 3.8 billion years without interruption. The story of how we got from the first living cells to the first human beings is the longest chapter in the history of life on Earth. It spans 3.8 billion years. It passes through every major evolutionary transition, the development of the nucleus, of sexual reproduction, of multicellular organization, of tissues and organs and nervous systems. Through the Cambrian explosion, when complex animal body plans first appeared. Through 5 mass extinctions, each of which wiped out the majority of species on Earth and opened new evolutionary possibilities for the survivors. We will not follow every step, but we will pause at the moments that matter most for our story. Approximately 375 million years ago, a lineage of fish developed the ability to breathe air and support their weight on modified fins. They became the first vertebrates to venture onto land. Their descendants would eventually become amphibians, reptiles, mammals, and ultimately us. approximately 66 million years ago, and an asteroid approximately 10 kilometers in diameter struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear weapons. The resulting fires, dust, and climate disruption caused the fifth mass extinction, the event that ended the age of non-avian dinosaurs. It also created the opportunity for mammals to diversify. The small nocturnal insect-eating mammals that survived the extinction began to radiate into the ecological niches left empty by the dinosaurs. Over the following 66 million years, they evolved into every form of mammal alive today: whales and bats and elephants and primates. Approximately 7 million years ago, a lineage of African primates diverged from the ancestors of chimpanzees. Over the following millions of years, this lineage evolved larger brains, upright walking, and eventually the capacity for language and abstract thought. Approximately 300,000 years ago, the first anatomically modern humans appeared in Africa. The atoms that had been inside stars, scattered by supernovae, drifted through space for billions of years, incorporated into the solar system, cycled through the early Earth, passed through billions of generations of living things. Those atoms had now organized themselves into something that could look up at the night sky and ask where they came from. Let us be specific about the atoms in your body, because the story is not just poetic, it is chemical. Your body is approximately 65% oxygen by mass, 18% carbon, 10% hydrogen, 3% nitrogen, and then smaller amounts of calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, and traces of many other elements. The hydrogen in your body is the oldest material in you. Hydrogen was made in the Big Bang 13.8 billion years ago. The hydrogen atoms in your body, in every water molecule, in every organic compound, have existed, essentially unchanged, since the first 3 minutes of the universe. They have never been inside a star. They predate the first stars. When you drink a glass of water, you are drinking hydrogen that is 13.8 billion years old. The oxygen in that same glass of water has a different history. Oxygen is made in stars, specifically in the helium-burning and carbon-burning stages of stellar evolution. The oxygen in your body was made inside one or more stars that lived and died before the sun existed. It was scattered by those stars' deaths, either in gentle planetary nebulae or violent supernovae, mixed into the interstellar medium, incorporated into the cloud that formed the solar system, and eventually, after billions of years of cycling through the Earth's chemistry and biosphere, ended up in you. The carbon that forms the backbone of every biological molecule in your body, every protein, every lipid, every strand of DNA, was made in the triple alpha process, a nuclear reaction that occurs in the helium-burning cores of aging stars. Every carbon atom in you passed through a stellar core. The iron in your blood, the iron in hemoglobin that carries oxygen from your lungs to your cells, was made in the final stages of a massive star's life, in the silicon-burning phase that immediately precedes a supernova. The iron in you was quite possibly made in the last hours of a star's existence, moments before it exploded. You are not a collection of atoms that happen to be alive. You are a temporary organization of some of the oldest and most traveled material in the universe. The atoms in your left hand may have been in a completely different star than the atoms in your right hand. The iron in your blood may have been forged in a star on the other side of the galaxy, from the one that made the carbon in your DNA. You are, in the most literal sense, assembled from the universe. Here is the part that is hardest to hold, but most important to understand. The atoms in your body are not yours. They were here before you. They will be here after you. They have passed through countless other organisms before reaching you, through bacteria, through plants, through animals, through other human beings. The carbon in your body has been part of the atmosphere, part of the ocean, part of the soil, part of other living things, many times over. And when you die, those atoms will continue their journey. They will be returned to the soil, to the water, to the air. They will be taken up by plants, eaten by animals, breathed in by other human beings. They will cycle through the biosphere for as long as the biosphere exists. Eventually, when the sun expands into a red giant in approximately 5 billion years, and the Earth is consumed or sterilized, those atoms will be scattered back into space. Some of them may be incorporated into new planetary systems forming around other stars. Some may drift through the interstellar medium for billions of years. Some may eventually fall into a new star and be fused into heavier elements. The cycle does not end. It has no end that we can see. What changes is the organization, the particular arrangement of atoms that constitutes you, your specific combination of carbon and hydrogen and oxygen and iron, organized into the precise structure of your body, running the specific chemical reactions that produce your thoughts and your memories and your experience of being alive. That arrangement is temporary. It is not permanent. It has never been permanent. Nothing in the universe is permanent in that sense. But the atoms themselves persist. They move from form to form, from star to planet, to ocean, to organism, to atmosphere, and back again, in a cycle that has been running for 13.8 billion years and will continue for billions more. You are a moment in that cycle, a particular arrangement, briefly sustained, that has the remarkable property of being aware of the cycle it is part of. Come back to your hand. You have been looking at it this whole time, in a sense. We began here, and we have been circling back toward it through 13.8 billion years of cosmic history. The atoms in that hand have been on a journey that makes every human journey look brief. They were forged in the cores of stars that died before the sun existed. They were scattered across space by explosions that briefly outshone entire galaxies. They drifted through the void for millions of years. They were incorporated into a young planet. They cycled through the chemistry of an early Earth. They passed through billions of generations of living things, from the first bacteria to the first animals, to the first humans, to the specific lineage that led to you. And now they are here, in your hand, organized into skin and bone and blood, running the chemical reactions that keep you warm and moving and thinking. This did not have to happen. There is no reason written into the physics of the universe why those particular atoms had to end up in that particular configuration. The universe does not aim at life. It does not aim at consciousness. It does not aim at anything. It simply runs according to its laws, and occasionally, in certain corners, under certain conditions, those laws produce something that can look back at the universe and understand it. You are one of those somethings, and that is not a small thing. It is, in fact, the most extraordinary thing we know of anywhere in the observable universe. Not the black holes, not the supernovae, not the dark matter, or the cosmic web, or the expansion of space-time. Those are vast and impressive and ancient. But they do not know they exist. You do. Step outside tonight, if you can. Find a place where the sky is dark enough to show stars. Look up. What you are looking at is not a backdrop. It is not decoration. It is not simply beautiful, though it is beautiful. What you are looking at is the factory, the forge, the origin of the material you are made of. Every star you can see is a nuclear furnace converting hydrogen into heavier elements. Some of those stars are dying right now, scattering their contents into the surrounding space. Some of that scattered material will eventually find its way into new planetary systems, new oceans, new chemistries, new forms of life that we cannot imagine and will never know about. The process that made you is still running. It never stopped. The carbon in your body was made in a star that you will never see and that no longer exists. The iron in your blood was forged in the final hours of a star's life, moments before it exploded with a force that briefly rivaled an entire galaxy. The hydrogen in every cell of your body has existed since the first 3 minutes of the universe, since before the first star, since before the Earth, since before life, since before almost everything. You are 13.8 billion years old, in the only sense that matters at the atomic level. You are made of the universe's oldest material, organized into its most complex known structure, capable of understanding the journey that brought it here. That is not nothing. That is, by any measure, we have everything.